Okay, this is lecture 2 of VLSI Devices 2025. Due to my business trip to Hong Kong, I have to pre-record this lecture 2 video. Okay, we start from the concept of density of states. So, density of states is shortly speaking those, and its expression is given here. Density of states means so how many states are there per unit volume and energy. So that's the reason why it is called as density, and this is density per volume and energy. So it has the unit like per cubic centimeter EV. So shown here. For example, here we have the density of states, and this is written as per electron and atom. So please note that there are about 5 times 10 to the 22 uh, atoms, silicon atoms per cubic centimeter. So it means that this number 1.0 and 0.5, this is quite close to 5 times 10 to the 22 states per electron volt cubic centimeter. Okay, so now let's come back to this expression. So density of states is obtained as just integration of states over given energy range. So simply speaking, how many states are there? So that will give us the density of state. And here we have a strange prefactor. So 1 over 2 cube of 2 pi, and that is originated from conversion form, just counting numbers into integration. So please review your previous lectures. So starting from the band structure, so here we have energy of an electronic state, and here we have a horizontal axis corresponding to k value. Then from this one you can count the density of states. So here you can see that there is certain energy range where no state electronic states are found, and this is actually forbidden zone, and this difference is called as band gap energy. So typically in the case of our silicon material, it is about 1.1 eV, and let's go to this one. Okay, now we have general expression for density of state. However, in the case of a silicon conduction band, it can be well approximated as a collection of ellipsoidal batteries. Actually, there are 6 copies of these ellipsoidal batteries, and for each battery, we can calculate the contribution to the density of state. So in order to calculate this density of state, actually we must calculate the volume in k-space. Why? Because this density of state expression involves the integration over k-space. This is k-space, and at a certain energy range. So not entire K-space, but the range between E and E plus EE. So in order to calculate this one, first of all, we have to calculate the volume of an ellipsoid whose the outer surface is corresponding to energy E. Then we can easily find that this is the volume of this ellipsoid. Why do we have this one? Here we have 4 pi over 3. This is a prefactor, and this is corresponding to the cube over a certain k value. Maybe you can ask me this question. Uh, this one is really an ellipsoid, not a sphere, but how can we apply the formula like this one for our ellipsoidal valley? But you know that here we have effective mass, which is not directly corresponding to the directional mass. By using this effective mass, actually this ellipsoid, while preserving its volume, it can be converted into a sphere. That's the reason why we can just use the expression for this sphere-like shape. So, anyway, this is the K-space volume corresponding to this guy, this ellipsoid, and if we increase it a little bit, E plus dE, then what will happen? So we can easily understand. Then by increasing energy value, so we will have a little bit expanded version of this ellipsoid. So by taking the difference between the volume corresponding to this red surface and this black surface, we can calculate the volume of a shell within a range between yes, E and E plus dE. Oh, so here we have minus EC because EC conduction band minimum is regarded as the starting point of our energy variable. So anyway, by doing this calculation, now we have this one. Simply speaking, you can just make first order derivative of this one with respect to uh, energy variable, then multiply this dE. Then that will give you the volume of a shell. In shell whose thickness is just dE. Then from this volume, then you can easily convert it into this density of state. The conversion factor was just 1 over cube of 2 pi. So now you can see that the density of state multiplied by this energy difference is simply given as this form. Here we have some quantity, and this quantity is corresponding to the cube of our effective mass, and here we have this form. This is constant for given energy structure, and only energy dependency comes from this E, and it's a square root. So when we just draw density of the state as a function of energy, electronic energy, so say that if this is n over E, then we will have the starting point corresponding to the conduction band minimum. After that, it will just follow the form of this square root form. Yes, so you will have this form for your density of state. Let's come back to the real density of states. So where can you find this kind of square root behavior? So this is exactly corresponding to this. Here we have a conduction band minimum. After that, this is corresponding to the square root of E minus EC. Okay, so now we know that density of states just follows the form of square root of energy, and it is because this 0.5 power is corresponding to the three-dimensional nature of our electrons in silicon. So if we consider two-dimensional electron gas or one-dimensional electron gas, the power will be just 0.0 or minus 0.5. So maybe you have seen it before in your previous lecture courses. Okay, so anyway, we will just concentrate on this three-dimensional electron gas. So we will use this 0.5 power. Then electron density can be calculated by just counting number of all occupied k-states. So here we must some selection of all occupied k-states, but by simple changing, so we can uh, do the same job with this form without any discrimination between empty states or filled states or occupied states. So you can just write down in that way. Instead, here we introduce a function called as distribution function, and it has this property. It is 0 when the state is empty, and it is 1 when it is occupied. So if we just adopt this form, then once again this, this summation is valid only for all occupied states. Yes, this is exactly the same one we wanted to have. So once we convert it to the summation of all entire k-space, after that, this summation can be easily converted into simply this integration. Of course, we must understand there is once again conversion rule between this summation and integration, and it is corresponding to this factor. And also we consider system volume. So please be careful the correct dimensionality when you convert one thing or summation to the integration. Oh well, now this is the number of electrons and this is volume. Then of course division of number of electrons by this system volume will give us the electron density. This one as the dimension of per cubic centimeter, and here we have this simple form. Simply speaking, we can just make the k-space integration of distribution function. Well, then if that is filled, then that will 0, and if that is empty, then that will 0. So it can be also written in a form like this. Yes, instead of the integral or entire k-space only occupy k-space, you can just integrate. However, this kind of selection over integration rate is quite difficult. So instead of that, we just make it here. And this integrand takes all kinds of complicated physics. So if we know now the distribution function, then we can easily calculate the electron density. So actually, calculation of this distribution function is quite important, and in general, it is not that easy to calculate this distribution function. But fortunately, if we consider the equilibrium condition, then it is known that this distribution function simply follows the Fermi-Dirac distribution. So it is given in a form of quite well-known form. So at first glance, it looks quite complicated, but by considering two extreme cases, we can easily understand this behavior. For example, if we have quite quite um, high end go to infinity, then what will happen? Regardless the value of this formula, then this term, the argument, input argument of our exponential function will go to very high. Then this exponential just takes this number and it is easily approaching to quite a large number. So 1 plus quite a large number will give us once again quite a large number. So eventually we rapidly approach to number 0. On the other hand, if we go to negative infinity, so then what will happen? So once again, this formula doesn't make any contribution, and this term will just vanish. So exponential of minus infinity approach to just number 0. So in this case, we will have the formula distribution corresponding to number 1. So simply speaking, if we draw the energy and formula distribution, what we can certainly say is there is certain extreme value 1 and another extreme value 0, and say that, for example, this is EF. If our energy is far away from this Fermi energy E sub F, then if we go too deep into this lower energy level, then we'll have just number 1. Fully occupied states. And if we go to much higher energy levels, then it will give us a completely 0, means that fully empty. Of course, in between here, we have a non-zero but not exactly corresponding to 1, and there will be certain value. So let's have a look at this actual formula distribution function. And here we have the number 0 as so EF. This is EF value. And if we go to the lower energy, it is rapidly approaching to the value of 1. And if we go to higher energy level, then it is also rapidly approaching to the value of 0. Of course, in between, we have certain transition from 1 to 0, and it looks quite smooth. So if we have just the number 0 corresponding to the formula level, then it is always number 0.5. Mention here, yes. So in this case, And if we go to a high energy, then this is rapidly decreasing. And low energy, it is rapidly increasing. And please have a look at, well, maybe within this energy and that energy range. So it is sufficient to have almost close value to 1 and or almost close value to 0. So simply speaking, if we have just a few, so please note that this is drawn at 300 Kelvin, so corresponding to the summer energy of 25 million electron volt. This is about 4 times kBT, and this is also 4 kBT. So if we are far from this Fermi energy level, away approximately 3 or 4 kBT, then we can say that our states are completely empty or completely um, filled. So roughly speaking. Okay, let's go to the next part. Um, Actually, we must consider Fermi-Dirac distribution, but um, can also consider another limit. So when energy is higher than Fermi level, of course, it means that E minus EF is a positive number. Then here we have positive argument for our formula distribution function. And since this is exponential and exponential is rapidly growing, so if our energy is a little bit higher than EF, then it will dominant. So comparison between this factor of 1 or number 1 and this exponent function, which one is dominant? Obviously, this exponential is dominant, so let's just neglect this part. Then we will have just exponentially decaying function as an approximate form of Fermi-Dirac distribution. I'm not saying that this is always correct, but when we have the energy level 3 times or of sufficiently larger than KBT, then this can be a good enough approximation for Fermi-Dirac distribution function. Here you can see this one. This is correct Fermi-Dirac distribution function. And this is the approximate form. Of course, you can see that the blue line and red line shows quite a big difference in, for example, this EF. Because, in this case, yes, we do not have this assumption. However, if we go to, for example, 50 millielectron volt, then we can see that the difference looks quite small. And if we go to even higher energy, yes, the difference becomes almost indistinguishable. Maybe you can ask me this question. Both of them are so small, so it is difficult for me to decide whether that is a really good approximation or not. So in that case, please just to draw your graph once again with semi-logarithmic scale. In this case, still x-axis is the energy scale within the linear scale, but the distribution function is drawn in the logarithmic scale. And you can see that here we have quite a big difference. But now, for example, above 50 electron volt, then the difference becomes quite small. For example, if we go to 4 times of kVt, yes, now the difference looks really negligible. So this is a good approximation for our Fermi-Dirac distribution function. Of course, we can consider another Boltzmann law, and when energy is sufficiently lower than Fermi level, then yes, actually this part, this exponential part can be fully negligible. Well, now when you make a comparison between one and this guy will give us, yes, this one is quite small and this one is just a constant. So roughly speaking, we can just treat it as number one. But how about the beyond this constant is? So here we have number one and quite small number. It's like this. If we have 1 over 1 plus delta, then if delta is quite small number, then we can make just a Taylor extension of this function. Then it is really good approximation for its original function. So simply speaking, so if our exponential term is quite small, then it can be just expressed as exponential something. This something is corresponding to this one. So if we go to quite a low energy limit, then okay, it can be quite well approximated. So in this case, let's have a look at this one. Of course, if we go to positive E minus EF, this is awfully uh, deviated from this Fermi-Dirac distribution. This is correct one, and this is our approximation. So of course it fails. However, if we go to lower energy level, so of course we will have a good um, agreement between Fermi-Dirac distribution and approximation. So these are called as Boltzmann limit. So sometimes we will just use, in many cases, this Boltzmann limit to make our calculation simple. By using this information, now let's try to calculate uh, carrier concentration. For example, electron density. We can follow similar way to calculate hole density P. So usually, let's come back to this one. The original expression for calculating electron density is given this way. However, in general, a distribution function is a function of k position, but at equilibrium, distribution function is no longer a function of every k point, but it can be just written as this form. Then now you can understand it can be converted into from this space integration to the energy space integration. And the conversion from k-space to the energy space is involved with density of state. So simply speaking, now this one can be converted into this form. N E, this is dose density of state and F over E. How can you make this conversion? Here, in general, K function, but it can be written as E function, energy function. and you can find it. And this kind of phase space integration converted into energy space integration. But in order to make this conversion correct, then we need this density of space. Yes, that's it. So now let's come back to our original lecture progress. Then, yes, this is the expression for our electron density calculation. Of course, we have to restrict our energy integration for this valid range of our approximation. So considering the lower energy level doesn't make any sense because density of states vanishes at that energy range. And now, so previously I have shown you that density of state just follows this square root form of electronic energy. Yes, that's correct. And here we have additional factors corresponding to the spin and Berry degeneracy. Um, Usually this spin degeneracy is fixed to number 2 and Berry degeneracy written in here as just a Z. In the silicon conduction band, this is corresponding to number 6. Okay, but we will just keep this general expression. And by using these two expressions, so density of state and equilibrium distribution function, you know that this is not exactly the Fermi-Dirac expression, but this is the simplified form under Boltzmann method. Okay, but it's okay. And collecting them all, just to put them there, then we will get this expression. Although it looks quite complicated, but here inside this energy integration, we just keep energy dependent functions and all kinds of energy independent functions are just collected here and we can just make a bookkeeping safely. And now we have this one. Yes. So simply speaking, it has the form of square root e exponential minus e kdt. Although it has Fermi energy and here some other quantity conduction band minimum, but basically it has the form of this expression. So now you can evaluate it quite easily. So I will just skip this one. Please check this one, and it can be easily calculated and it gives you just a number. Yes. So using this number, so simply speaking, this integral function gives a number. So electron density is now given as certain coefficient and exponential of EC minus EF and another number. So the main conclusion of this evaluation is electron density just follows the form of exponential minus EC minus EF K B T. Simply speaking, if conduction band level is far away from Fermi level, then this value is quite large and it means that lower electron density. Or if we have the relatively small difference between conduction band minimum and Fermi level, then this number is small, so it's minus exponential function. exponential of minus this input output is now increasing, so we will have a higher electron density. So if we just keep this EC point and changing the EF level, then this is the direction to increase electron density, and this is the direction to decrease electron density. So if we can, by any means, change the position of EF from here to there, then we can also change the number of electrons exponentially. That is the main lesson taken for this evaluation. So now we know that electron density is simply given as certain number and energy dependent form. So energy here energy means that so conduction band minimum energy and Fermi level. Then this coefficient is too long to be memorized, so instead we just introduce a concept of effective dose, and it is the entire term here is just written as effective dose of conduction band. Of course, we can define similar quantity like V, so this is corresponding to the valence band, and this is the effective density of state of conduction band and valence band. And please don't be confused with the dimensionality. Usually when you say the density of state, this one is per EV and volume. However, NC itself or NV itself, they have just per cubic centimeter quantity. Energy dependency is just integrated, so we will have just density, volume density as an effective dose. Although the name is dose, but energy dependency does not exist. So here you can see this expression, and when you have a look at the conduction band and valence band effective dose, you know that these numbers are orders of 10 to the 19. So of course, although here we have a little difference, yes, there is a factor of almost a factor of 3 difference here, but this is not that high. For example, if we have a look at gallium arsenide here, you know that conduction band and valence band shows much different NC and NB. Of course, NB is much higher than NC, and so compared with the gallium arsenide, silicon seems to be more balanced between conduction band and valence band in its effective dose values. Okay, so now since this one is this complicated expression is just written as NC, yes, we have quite a simple expression. I have already stressed this form. Okay, so if we have a small difference between EC and EF, electron density is increasing. Also, for hole density, we can find a similar one. If we have relatively close EF to valence band maxima, then we will have a higher and higher hole density. Okay, but here you can see that NC and NV, so they can be just converted into one single quantity called as Ni. So in this case, let's consider intrinsic case. Intrinsic has many different meanings in many different contexts, but in this case, intrinsic means that we don't have any defects or impurities in our silicon material. This is pure silicon. In this case, how many electrons are there and how many holes are there? Actually, we don't know exactly yet, but what we can say is electron density will be the same to the hole density. Why? Why do we have this one? Because previously here we have a conduction band, the valence band, and in this case, if we don't have any impurity there, then the only way we have electrons in this conduction band is just to moving one electron from valence band. So means that generation of one electron is always involved with or related with the generation of a whole. That's the reason why we can say that in this case, electron density and hole density are the same. So if we adopt this condition, then this is the expression for electron density, and this is the expression for hole density, and they should be the same. Please note that Nc and Nv are given numbers and we assume a constant temperature, for example 300 Kelvin. Then we can make certain manipulation. So from this above equation, now we can introduce a certain electron density and hole density at this intrinsic case, and it is simply given as this expression. So when you have a look at this expression, you have the different energy difference between conduction band minima and valence band maxima, and that is usually called as band gap energy. So okay, here I have a typo here, so I will fix it. Here we have a half of it. Okay, then then the temperature dependence of Ni has quite a sensitive form to the temperature. So here, mm, although Nc and Nv have also temperature dependence, but it is not that dominant. But when you have a look at this one, here we have bandwidth energy and also divided by this thermal energy, and more or less this bandgap energy has almost independent to the temperature. But still, here we have the term exponential minus t. Here we have a quite severe temperature dependence. So intrinsic carrier density is quite a sensitive function of temperature. For example, where can you find 300 Kelvin? Yes, 300 Kelvin. We have this value for silicon, roughly speaking, that is corresponding to 10 to the 10 per cubic centimeter. However, if we go to quite low temperature, for example, here you see that 4, this is corresponding to 250 Kelvin, then this is already shows much lower intrinsic carrier density. So carrier density is quite a sensitive function of temperature, but at least for our own purpose, please remember this number 10 to the 10 at 300 Kelvin. That will be quite useful for your next study. Okay, then using this intrinsic carrier density instead of NC and NV, then now carrier densities can be expressed in this way. Electron density is proportional to the Ni and exponential of something. Of course, electron density follows this form, this dependency. KBT EC minus EF. However, this EC can be easily converted into EI plus EC minus EI. This is just a given number, so instead of EC, we can write down here in terms of intrinsic form level. So we have a more frequently used form like this. Please remember these two forms. We will use this form in our later study. Of course, once we have this form by multiplying n and p expression, the left-hand side gives us n times p, and the right-hand side gives us ni squared, and this and that has just a negative and positive same argument, so they are cancelled out. So the product between n and p are more or less constant, a square of ni. So please remember also this expression. Okay, up to now, I just consider this intrinsic case, but more practically important case is extrinsic case. Extrinsic means that we intentionally introduce a certain impurity atoms, non-silicon atoms, into the silicon crystal. So then what will happen to our silicon crystal system? Please note that even when we introduce 5 times 10 to the 20 impurity atoms per cubic centimeter, this is a quite high impurity density, but this is just 1% of a silicon atom. So 5 times 10 to the 22 per cubic centimeter. This is the number density of silicon atoms in silicon crystal. So although we have impurities quite high, like 10 to the 20, but this is still below 1%. So instead of alloy, they can be just regarded as impurities. The vast majority of this system is still silicon, and only occasionally we can find the impurities, so it does not change the overall band structure of silicon. So in this case, our impurity atoms introduce a certain additional energetic states in the silicon forbidden zone. So this is a conduction band minima, and this is a valence band maxima. And here we have forbidden zone and certain impurities introduce given energy levels. For example, we know some impurities widely used in the manufacturing. So that is corresponding to arsenic, phosphorus, and boron. So please find out them in this list. So you can see that arsenic, phosphorus, and boron. In this case, now phosphorus and arsenic introduce some additional state quite close to the conduction band minimum. And in the case of boron atoms, they introduce a certain energetic level, additional one, quite close to the valence band maximum. So in this case, the electrons originally located in this phosphorus atom or arsenic atom can easily move into the conduction band, so they can be used as donors, electron donors. And also in the case of this boron, they can accept electrons inside the valence band. So they can be used as acceptors of electrons. So it can be used as a p-type dopant. Of course, we can find other materials or other atoms, and they also introduce many different levels in this forbidden zone. They are not usually used in our silicon manufacturing technology because they introduce some states quite far away from this EC and EV. So it means that they do not have sufficiently high probability to contribute electrons or capture electrons from our conduction band or valence band. So in engineering sense, this is not a good way to modulate the electrical conductance, so they are not preferred. So in this case, now by introducing these impurity atoms, our Fermi level will be changed correspondingly. So in this case, what will happen? Think about a homogeneous system. So this is just uniform, and we have introduced the donors whose volume density is just ND. So then what will happen? Since this system is really homogeneous, so now we assume a local charge neutrality. So we assume this kind of charge, local charge neutrality. It means that um, electron density minus and hole density plus and positively ionized donor density. Sum of these three numbers should vanish because electrons are contributing negative charge and hole contribute positive charge. Also, ionized donor contribute positive charge. So simply speaking, the sum of these three numbers or three densities is net charge density at a certain point that shouldn't vanish. If they don't vanish, what will happen? If they don't vanish, then we must consider this silicon, doped silicon is, for example, positively charged or negatively charged. And let's say that we have a silicon chunk there, okay? There's a small piece of silicon, and we are far away from that silicon, but we have to feel the electric field generated by this small doped silicon. That is not possible. Actually, we have to have neutrality because otherwise we have quite a strange behavior. So now once again, if we have a look at this tower 2 equation 2.19, so you know that this is corresponding to hole density minus, and this is corresponding to the electron density, and finally we have ionized donor density. But for shallow donor impurities, we can say that these donors are almost completely ionized. So now we can write down in this way. And also, how about this n-type proton? Compared with the electron density, the hole density would be quite small. So just to neglect this term. So now we have this expression. This expression is nothing but minus n plus fully ionized donor density should be the same. Hmm. It means that actually we are assuming that electron density equal to just to ND. Yes. In this case, what will happen? In this case, from this expression, now we introduce the expression for electron density in terms of the conduction band minima and formidable, and you can find out this relative position of formidable with respect to the conduction band. Also, when we have this number, electron density is given as ND, then since we have the simple law, NP product is equal to square of intrinsic carrier density. So since N is approximated as ND, so whole density will just follow this number. For example, if we have quite a high density, like 10 to the 20 per cubic centimeter, then our whole density would be just number 1 per cubic centimeter. Because Ni is more or less 10 to the 10, so square of it, it will become 10 to the 20. So uh, when we make a comparison between donor density and hole density, there is 19 orders of magnitude difference between electron density and hole density. So our original assumption that hole density is negligible, that is quite much justified. Okay, so now previously we introduced Ni and Ei into the formula to express our electron density and hole density. By using that expression, you can easily find this form. Okay, so this form are quite useful, and also this form is quite useful for p-type of bond where acceptors are dominant, and here n-type of bonds donors are dominant. Okay, I think that that's it for today's lecture, lecture 2. Please note that this is not my usual lecture style. So usually I wanted to make more detailed expressions, but please note that this course is not the first course for semiconductor device physics. I assume that you have already attended some courses, so this is just to provide as a quick review of these equilibrium properties. So if you don't understand these contents, then please review your previous lectures. So in the next lecture, once again, pre-recorded one, in lecture 3, we will consider the transport mechanism inside the semiconductor materials and devices. And thank you for your attention. Bye.